Assalamu alaikum. Bismillahir Rahmanir Rahim. I welcome you to the 32nd lecture for the series of lectures on advanced computer architecture. Today, our focus will be on the main memory and virtual memory designs. After a brief review of what we have been talking since our 25th lecture regarding the memory hierarchy design, we will discuss in details the main memory design and its performance, and then we will take up the virtual memory system design. In the 25th lecture, we introduced the goals of memory system design for high performance computers, and we noticed that a memory system designer aims to present to the programmer as much memory as is available with the cost which is as low as the cost of the cheapest memory available, and the speed as fast as the speed of the fastest memory provided by any technology. In order to achieve this goal, and considering the increasing gap between the speed of the processor and the speed of memory, different types of memories are organized in several hierarchical forms. The fastest, smallest, and most costly memories are placed either within the processor or closest to the processor chip. That is, at the uppermost level in the memory hierarchy, the memories are placed very close to the processor, and these memories are smallest in size. The slowest, biggest, and cheapest memories are placed at the lowest level in the memory hierarchy. Furthermore, by taking the advantage of principle of locality, the memory hierarchy designer provides the user an average access speed that is very close to the speed obtainable by the fastest technology, and it provides the cost that is very close to the cost of the cheapest technology. Now, so far, we have discussed that the semiconductor memories, such as the static random access memories and dynamic random access memories, they are placed at the upper levels in the memory hierarchy, such as the static memories are used as caches and dynamic random access memories are used as the main memory. We also noticed that the static random accessor memories do not require any type of refreshing. Therefore, such memories are fastest, but they are expensive because they require much more number of transistors to implement them. At the same time, the dynamic random access memories, which are used as the main memories, they need refreshing. Therefore, they are relatively slower. Now, at the next level of the memory hierarchy, the magnetic, optical, or other medias such as hard disk, compact disk, or tapes are placed farthest away from the processor, and in the memory hierarchy, such memories are referred to as the virtual memory. The cache and main memories are organized in equal sized blocks, and data transfer between the CPU and cache takes place as the word transfer, and that between the cache and the main memory, it takes place as the block transfer. Furthermore, the CPU requests the contents of the main memory location from the cache controller, and the cache controller checks the cache block for this data. If the requested word is present in the cache, that is, it is a request hit, then the word is transferred to the CPU. And this shows that the word transfer is fast. Whereas if the requested word misses, it results in a miss penalty, because the required word is to be read from the memory to the cache, and then the word is to be transferred from the cache to the CPU. Now, so far, we have been discussing different cache designs and their impact on the performance of the computer. This performance is measured in terms of the average memory access time. And we have also been discussing different techniques to reduce time to enhance the performance of the cache and hence the performance of the computer. Now, with this much discussion about what we have been talking about the design of the cache and its impact on the performance of the processor, then let us talk about the main memory organization and see how it affects the overall performance of the computer. The main memory, which is the next lower level from the cache in the memory hierarchy, it fulfills the needs of caches, and it serves as source for caches and destination for the secondary or the virtual memory. Now, in order to understand the design of random access memory, which is used as the main memory, let us have a look on this organization of a 4 megabit DRAM, which is used as the main memory. Here, note that the storage cell of a DRAM are organized in array form with number of cells in each row and column equal to the square root of the total number of bits. For example, in this block diagram, you can see that the cells of 4 megabit DRAM are organized as 2K by 2K bit array. Furthermore, the addresses are divided into 2 parts, that is, the row address and the column address. One of the addresses is sent at a time to reduce the number of address pins. However, inside the chip, we use a multiplexer-demultiplexer circuit so that the number of pins may be reduced at the periphery of the chip. The row decoder shown here, it affects the latency, while the column decoder, it affects the overall bandwidth of the memory. Internally, it might use banks of memory arrays. For example, the 4 banks of 1K by 1K bit or 16 banks of 512 by 512 bits can be used in order to design a 4 megabit memory. Normally, a memory is packed in dual inline module, which is also known as the DIMM model. The performance of a dynamic RAM chip has always been important for the system designer, as a system designer likes to use fewer number of chips per system. As a result, several improvements have been made to the design of the main memory. These improved designs are fast page mode DRAM, synchronous DRAM, and double data rate DRAM. The fast mode DRAM is designed to optimize sequential access by exploiting the row buffer, whereas the synchronous DRAM avoids need for handshaking between the chip and the memory controller, and the double data rate DRAM transmits data from chip on both the falling as well as the rising edges of the clock signal. Now, let us see what are the matrices which can be used to measure the performance of a main memory. The latency and bandwidth are the most important and commonly used matrices to measure the performance of main memory. Here, the latency deals with the average memory access time, whereas the bandwidth depends upon the number of bytes read or written per unit time. The latency of main memory is mainly the concern of caches, as it determines the cache miss penalty, which is measure of access time and the cycle time. As we have already discussed that the access time is the time between request and the word access, and the cycle time is the time between requests. Whereas the bandwidth has an impact on the performance of inputs and outputs and the use of multiprocessors. That is, the caches are inserted in low latency memory, and the input, output, and multiprocessor demand higher bandwidth. However, as we have already noticed that the main memory bandwidth is also important to multi-level caches, because we know that the second-level caches with larger block size demand large number of bytes read, write per unit time. So far, we have been discussing different cache organizations to reduce the CPU and DRAM gap. Now, let us discuss the methods used to improve the main memory bandwidth. The most commonly used techniques to improve the main memory bandwidth are the wider main memory, simple interleaved memory, and independent memory banks. Now, let us discuss these techniques one by one. First of all, let us discuss what do we mean by the design of wider main memory. Before we have a look into the design of wider main memory, let us see the simple organization of one-word memory system, where everything is one word wide. That is, the cache, the CPU cache bus, the main memory, and cache memory bus are all of one word in size. That is, of 8-byte wide. The simplest possible method to improve the main memory bandwidth is to make the memory wider. That is, double or quadruple the width of the cache, which allows read-write of 2 or 4 words per unit time. Let us have a look onto the simple design of a wider memory. Here, the organization of 4-word wide memory is depicted, where a 4-word wider L2 cache is used with the narrow 1-word L1 cache. That is, the level 2 cache, which is interfaced with the main memory, is wider, whereas the level 1 cache, which is interfaced with the CPU, is shorter. The CPU to level 1 cache bus is 1 word wide, and the level 2 to main memory bus is 4 word wide. And a multiplexer is used to interface the wider L2 cache with the narrower L1 cache. In order to see how the performance of CPU is improved and what is the impact of this design on the bandwidth of the memory. For this, we can consider this example where a timing model of memory system comprising caches having 4 words block, where each word is of 8-byte, so 4 word mean 32-byte. The timing model says that the time to send an address is equal to 4 clock cycles. The time to send the data word is also 4 clock cycle, whereas the access time per word is 56 clock cycles. Now, let us evaluate the miss penalty and bandwidth for 1-word and 4-word wide memory system and see how the wider bandwidth improves the performance or reduces the miss penalty. In order to solve this problem, let us define the miss penalty of memories. The miss penalty of memories can be expressed as the product of number of words and the sum of time to send address, time to send data, and time to access words. Using this definition of the miss penalty, for 1-word organization, the miss penalty can be calculated as 4 multiplied by 4 plus 4 plus 56, where the first 4 is corresponding to the 4 words of the memory. Here, this results in a value of miss penalty to be equal to 256 clock cycles. And as we know that we have already said that these 4 words will be of 32-byte, therefore the memory bandwidth is 32 by 256, which is equal to 1/8 per cycle. Whereas for the 4-word organization, the miss penalty can be expressed as 1 multiplied by 4 plus 4 plus 56. Here, 1 is used because for the wider memory, all the 4 words are sent at a time. Therefore, it results in a value of the miss penalty to be equal to 64 clock cycles, and it gives us the memory bandwidth to be equal to 32 divided by 64, which is equal to 1/2 bytes per cycle. So from this, we can conclude that 4 times wider memory reduces the miss penalty by 4 times and it enhances the bandwidth by 4. Now let us see what are a few demerits of the wider main memory. As you can see from the organization of the memory diagram, that multiplexer is the extra cost for interconnection between the CPU and the memory. As we mentioned earlier, a multiplexer is essential to select a word and hands over this word to the L1 cache. The other demerit of wider memory design is that if the main memory is to be expanded by the user, it must be expanded or incremented as double or quadruple. That is the same as the memory width. This means that we have to place some larger chips in order to expand the memory, and we cannot work with smaller sized memory chips. Now let us talk about the interleaved memory design. An alternative approach to increase the bandwidth of main memory is to organize the memory chips in banks to read or write multiple words instead of one word at a time. Here, a 4-word wide interleaved memory organization is shown, where you can see that the address mapping assumes that the addresses of the 4 banks are interleaved at the word level. That is, the bank 0 has all words whose address can be given by the address mod 4 to be equal to 0, whereas the bank 1 has all words whose address mod 4 is equal to 1, and the bank 2 has all words whose value of address mod 4 is equal to 2, and the bank 3 has all words whose address mod 4 results in a value equal to 3, which means that the banks are placed and accessed in a sequential order from, if we have to have the first word can be obtained from the word address 0, 1, 2, and 3, which is associated with the bank 0, bank 1, bank 2, and bank 3. So also note that in this arrangement, as all the banks are of the same width, so the width of the bus and the cache is also same, which facilitates to send same address to all the banks simultaneously. And it permits a read-write of a word at the same address of all the banks sequentially. That is, the interleaved memory is logically a wide memory, except that the access to banks are staged over time to share the internal resources. Let us consider an example which we considered earlier and see how the same example and the same timing model can be used for interleaved memory. Here, the miss penalty for 4-word interleaved memory can be expressed as it is equal to the time to send the address plus the time to access plus the product of the number of banks and the time to send data. By substituting the previous values, it results in 4 plus 56 plus 4 multiplied 4, which is equal to 76 clock cycles. This results in bandwidth equal to 32 by 76, which is approximately equal to 0.4 bytes per clock cycle, which is giving us an enhancement of 3 times as compared to the one-word wide memory, which has got a bandwidth of 32 divided by 256 equal to 0.125 bytes per clock. These two examples show that the wider memory and interleaved memory enhances the bandwidth of the main memory. Now let us consider the third technique, that is independent memory banks. This technique is basically the generalization of interleaving memory banks, which is used to enhance the bandwidth of the memory. Here, the memory banks offer independent access instead of faster sequential access for the interleaved memory. This approach is quite useful for the applications such as multiprocessors, IOs, CPU with hit under n misses, or the use of non-blocking caches. Here, in this case, the memory is organized as superbanks of number of banks, where bank is defined as a portion within a superbank that is word interleaved. This diagram shows here the superbanks that has separate addresses and possibly separate data lines, whereas the banks are interleaved memories, as we have discussed earlier. Here, the banks are organized to share their address lines with the memory controller, enabling each bank to use the data portion of the memory bus. Furthermore, all memory in a superbank is active on one block transfer, or we can say a bank transfer. This arrangement is the generalization of interleaved memory that allows multiple independent accesses. That is, the input device can use one controller and one bank. The cache read may use another one, and the cache write may use the third one. The non-blocking caches is an example of independent memory bank organization because it allows multiple cache misses to be serviced simultaneously. Now, with this much discussion, on to the 3 different approaches to enhance the bandwidth of the main memory. Today, we have discussed these techniques where we have noticed that the higher bandwidth is available by using the memory banks or by making the memory and its bus wider, or doing both. Furthermore, an important consideration for the designer of interleaved memory is to decide that how many banks should be there in order to use the memory efficiently. This decision is essential to ensure that if memory is being accessed sequentially, for example, when we are processing an array, then by the time you try to read a second word from a bank, the first access has finished. Otherwise, it will return to the original bank before it has the next word ready. Let us discuss this with the help of an example and see how a designer decides the number of banks. For this, let us assume that we have a memory which has got 8 banks, each of 64 bits, with access time of 10 clock cycles. Here, note that starting from cycle 1, the CPU could get a word from bank 0 after every 10 clock cycles because the access time is 10 clock cycles. Now, after the 10 clock cycles, the bank 0 would begin fetching the next desired word, and the CPU would receive the word from the following 7 banks sequentially till the 18th clock cycle. The 8 clock cycles are for the first 8 banks, whereas the 10 clock cycle is the total access time. Therefore, it has to wait for 2 clock cycles. Hence, the CPU cannot start fetching until clock cycle 20, as to complete the next access, it requires 10 clock cycles again. This shows that to avoid the waiting period of the CPU, the number of banks should be equal to or greater than the access cycles, that is, in this example, 10. Therefore, we can summarize by saying that for interleaved memory, the number of banks should be greater than or equal to the number of clock cycles to access the word in bank. So far, we have been discussing different cache and main memory organizations and their impact on the performance of a computer. Now, considering the memory needs to run multiple processes, each with its own address space, it is too expensive to dedicate a full address space from the main memory to each process. And at the same time, the address space of a single process or the sum of address space of multiple processes may exceed the physical memory available. Furthermore, the increasing gap between the CPU and memory speed, the high cost of main memory, and more demand of memory space to run multiple processes provoked the use of physical DRAM as a cache for the disk and share the physical memory among processes. This means that the use of disk and main memory such that it appears to the programmer as a single level storage, where the mandatory transfer between the main memory and the disk takes place automatically. Note that this single level storage space and its management does not exist physically. Therefore, this memory is defined as the virtual memory system. A virtual memory is made available to the programmer, which automatically manages two levels of memory hierarchy, that is, the main memory and the secondary storage. Virtual memory, in fact, divides the physical memory and the disk into segments. Sometimes these segments are also named as pages. Furthermore, the virtual memory segment is called a page to distinguish a segment from the segment as used in the cache and named as block. However, in the virtual memory system, contiguous pages in virtual memory are allocated to different processes. Further, in order to understand the concept of virtual memory system, let us have a look onto the system diagram for the virtual memory. Here, a 16K byte program is divided into 4 pages, each of 4K byte, and is logically placed in 4 contiguous blocks in the virtual address space ranging from 0 to 16K, whereas the actual location of 3 pages named as A, B, and D may be in the physical main memory, and 1 page named as C is located on the disk. Here, multiple processes may be resident in the main memory and disk, with each process occupying its own address space, and only the active code and data is actually made available in the main memory, where the memory is allocated to process as needed. The other attributes of virtual memory are the protection and relocation. Let us discuss the protection first. Virtual memory provides protection against interference of one process with another, because here different processes operate in different address space, and different sections of address space have different permissions, and the user processes cannot access privileged information. This is shown here in this page table, where you can see that the virtual page permission for read and write is shown here in the first 2 fields. Now let us talk about the relocation. Virtual memory also simplifies the loading of program for execution using a mechanism called relocation. The relocation is a process that allows to place a program anywhere in the physical memory or the disk just by changing the mapping between them. Furthermore, relocation can be implemented by hardware as well as by using software techniques that change all the addresses in a program each time it runs. Now, with this much discussion on to the attributes of virtual memory, let us talk about some terminologies which are used in virtual memory system vis-a-vis the terminologies used in cache memories. The terminology page or segment is used in virtual memory corresponding to the block used in cache memory. However, the fixed size blocks in virtual memory are referred to as pages, and the variable sized blocks are known as the segments. Furthermore, the terminology page fault or address fault is used in virtual memory corresponding to the misses in cache. The CPU produces virtual address as it produces main memory address for the caches. The virtual addresses are translated to the main memory or the physical addresses. The process of address translation is analogous to the memory mapping as used in caches. However, the mapping of a virtual address to the physical address is performed through a data structure which is known as the page table. The data structure contains the physical address of the segment or the page. The other differences between the caches and the virtual memory are: number one, replacement on the cache miss is controlled by hardware, whereas the page fault in case of virtual memory is controlled by the operating system. Second, the size of the processor address determines the size of virtual memory, whereas the cache size is independent of the processor address. Third, the secondary storage is also used for file system in addition to acting as the lower level backing storage for the main memory. However, the file system occupies the space on secondary storage and is not on the virtual address space. Now let us talk about some issues of the virtual memory design. The first and the most important issue is that if memory is to be organized similar to a cache, then how should we set different parameters of the design? For example, the line size, which is to be large in this case because disk is better at transferring larger blocks. Secondly, the associativity. In case of virtual memory, the associativity should be very high. We usually prefer to use fully associative structure for the placement of the data. And this method basically reduces the miss rate. Furthermore, we have to find out what should be the right strategy. The right strategy should be either write through or write back. We usually prefer write back because we cannot afford to perform small writes to the disk, as miss penalty to write on the magnetic media is very high. The other issue is to determine what would be the impact of different choices such as the miss rate, hit time, miss penalty, tag storage, and some other overheads in case of the virtual memory system design. Here we can say that the miss rate is to be extremely low. Hit time must match the cache or the main memory performance. The miss penalty is usually very high, and the tag storage overhead is low relative to the block size. With this much introduction about the virtual memory system, let us have a look onto a typical virtual memory system which is used in workstations, servers, or modern PCs. Here you can see that the CPU generates the virtual address. The operating system manages a lookup table, which is usually referred to as the page table. The lookup table contains the location of the page or segment on the disk or in the main memory. And the hardware converts the virtual addresses to the physical addresses, whereas the operating system manages the lookup table. Now this diagram shows what happens in case of page fault. If an object is on the disk rather than the memory, this situation gives rise to a page fault. Here you can see that the page entry table indicates the virtual address, whether it is in the memory or not. If it indicates that it is not in the memory and the operating system exception handler is invoked, and this exception handler then moves the data from the disk into the memory. While moving this data from the disk to the memory, the current process is suspended and others are resumed. And in this particular situation, the operating system has full control over the placement. Here you can see that the lookup table shows that page A and B are on the disk. The operating system moves the data to the main memory, and the contents of the page table are updated. Now let us see step by step how a page fault is serviced. A page fault is serviced in 3 steps. The first step is to initiate block read. Here, the processor signals the controller to read block of length equal to the page length, starting at a disk address, say X, and store it into the memory at the starting address Y. The second step is the DMA transfer, that is the direct memory access transfer. At this stage, the read occurs. The control is handed over to the DMA controller, and the required data is read from the disk and is transferred to the memory. Whereas the third step is to complete the read operation, and at this stage the I/O controller signals the completion. It interrupts the processor and the operating system resumes the suspended processes. So this way a page fault is completely serviced. Today we have talked about the main memory design, where we have said that the main memory is used at the next door level in the memory hierarchy from the cache. We discussed different techniques such as the fast page mode, the synchronous DRAM, and double data rate DRAM as the improvements for the design of main memory. We also discussed 3 different methods to enhance the bandwidth of the main memory, which plays a very important role in enhancing the performance of the computer. These techniques include the wider main memory, simple interleaved main memory, and independent main memory. Then we introduced the concept of virtual memory system. Here we defined some new terminologies as compared to the terminologies being used in cache, and then we discussed the sequence in which a page fault is handled. Now, with this much discussion today, I stop here and say you Allah Hafiz.